Howdy, I'm Matthew Ebert, and I'm part of the MIDL lab led by Dr. Vinayak Krishnamurthy, and I'm here to share our work on design methodology for statistically self-similar structures. This work involved two undergraduate students, Noah Hill, who's the lead author, and Mena Maurice. I'd like to motivate this work through an example from nature. If we look at different leaves, say from an oak tree, each individual oak leaf is unique in terms of its exact form. However, all oak leaves belong to a family. They share similar characteristics, not just in terms of their shapes, but also in terms of their functionality in providing nutrition to the plant. And we see this across all trees. All mango leaves belong to one class, but no leaf is identical. Our motivation in this work was to investigate this motif of distinct feasible functional solutions within a common structural family as a means for generative form exploration. This has been done in the past in order to create alternatives for brackets, where a designer specifies the loading conditions. In a similar manner, generative design in combination with topology optimization has been used to create alternatives for wheel designs. In this case, creating multiple wheels while managing the trade-off between cost, novelty, and compliance. These generative design methods have relied on solving some sort of inverse design problem, which can be expensive to solve and not allow for any tuning of the results. The objective of this work is to investigate a forward design methodology for creation of similar but distinct structure creation. We take inspiration from fractal geometry. Fractals can be defined by their self-similarity regardless of scale property. In this case, the Sierpinski triangle can be seen by infinitely zooming in. This idea has been used previously to create various truss structures based on different types of fractals. Here the top one is based off that Sierpinski triangle. Other methods have directly tested fractal structures' buckling resistance in several different configurations. There are also extensions in the same way to create 3D fractals using a tetrahedron, which you can see in that bottom left-hand corner. The compression strength of various iterations of fractals have also been tested in some very recent work published in January of this year. These methods are all forward design explicit methods, where the exact fractal is defined through some sort of geometric properties, and then tested. In this case, you can see here H, T, L, those kind of parameters are explicitly defined. These approaches do not create families of similar structures, but rather each structure is unique. For our approach, our goal is to use a forward design method, which can also create families of structures that are similar geometrically. The basic idea behind our approach is to generate points based on an algorithm known as the chaos game, followed by Voronoi tessellation of the points, taken as Voronoi sites to get a cellular structure, and then adaptive thickening of the edges of the Voronoi cells to obtain the final structure. So let's take a look at the chaos game, which we use to generate our sites. We start with a convex polygon, in this case an equilateral triangle, and then a point which can be located inside or outside of that polygon. In this case, it's that orange point on the upper left-hand corner. Using this point as a start, we randomly select a vertex and move towards it with that random point. In this case, we select that lower right-hand point of the equilateral triangle. We move towards that random vertex and then repeat the process, each time choosing a new random vertex and moving towards that random vertex using the previous point. This creates a recursive algorithm, so every time we create more and more points and add them to a set. As this happens more and more, we start to see the fractal structure appear, which in this case is the Sierpinski triangle. The key observation to make here is that every time we start with a random seed point, we get a different set of points for a finite number of iterations. This is what provides stochasticity to our method. Now we take the points and compute a Voronoi tessellation. A Voronoi tessellation starts with a set of points, often called Voronoi sites, which create cells where every point in a cell is closest to that cell's original seed point. Another way of visualizing this is with these circles, expanding from points until they collide with one another. In order to generate the final structure, our final step is to thicken the edges of the Voronoi tessellation. The main challenge here is that the areas of the Voronoi cells decrease hierarchically based on the fractal geometry. To address this, we perform an adaptive thickening operation that computes the thickness of each edge based on the areas of the cells that share that edge. Simply put, cells with larger areas have a larger thickness, and smaller cells have a smaller thickness. For more details, please refer to our paper. So let's look at some different types of structures that can be generated based on the parameters of our method. While we've seen the Sierpinski triangle in the past few examples, we can change lambda. This is that distance traveled to the randomly chosen vertex. With a very low lambda, or fractional distance, we don't get much of a fractal property, since the points don't change much on each iteration. But with a large lambda, the points tend to cluster towards those polygon vertices. We can also vary the number of points in the starting polygon. In each of these cases, it's a regular polygon. We have also chosen a lambda in order to see the fractal property at each n. The number of iterations also affects the structure. With a very low number of iterations, the fractal structure is not very clear, unless you're really looking for it. However, as the number of iterations increases, the fractal structure becomes more apparent. With even higher number of iterations, the Sierpinski triangle becomes evident. The beauty of this method comes through the generation of multiple iterations. Using the same set of parameters, in this case Sierpinski triangle with 750 iterations, we obtain many different structures, which are all related through their generation parameters, but are distinct. This gives similar but distinct structures. This is because each time we generate points, the starting random point and the randomly chosen vertex at each iteration changes. This is exactly what we mean when we call these structures statistically self-similar. Each of these structures are distinct, but belong to the same family. The question that we would like to ask is, if these geometric similarities cause similar mechanical properties. In order to explore this question, in this work, we choose modal analysis to see if we get self-similarity in terms of mechanical behavior. With modal analysis, we fix the boundary. The natural frequencies of the structures are directly related to the geometry of the structure, since any change in geometry changes the natural frequencies. These natural frequencies allow for statistical comparison between structures. Our first test involved generating 100 structures, using the same set of parameters and recording the first 10 natural frequencies. This would allow us to determine if the geometric similarities carry over into similarities of mechanical behavior. We use a Sierpinski triangle for this test. Through ANOVA tests, we can determine that the population means of the different modal frequencies are statistically different. Since each frequency is from distinct populations, we can conclude that these structures' geometry does lead to a correlation in mechanical behavior. This answers the main question of this work and shows that we do get self-similar mechanical behavior from stochastic self-similarity. We also observe the low standard deviation of each frequency, meaning there is not much varying the natural frequency for each structure. We also observe pairing of results, where mode 1 and 2 are similar in value and mode shape. Similarly, modes 4 through 6 are similar, and modes 7 through 10 are also similar. Our second test involves changing some parameters. We set t as 170 iterations, and change n, which is the number of sides of the polygon, as well as that fractional distance lambda. Using these parameters, we only look at the first 5 natural frequencies, with the goal of determining the relationship between fractional distance and natural frequency. So let's first look at the triangle. First, let me explain this graph. For each value of fractional distance, we have the first 5 natural frequencies, which are represented by the different colors. The box and whisker plot shows the median and standard deviation in the box, and the maximum and minimum represented by the whiskers. All outliers of the results are shown as points. At each fractional distance, we tested 30 structures, so in total this graph shows 270 structures and their first 5 natural frequencies. There's a few things to note with our first test. Firstly, we see a nonlinear relationship between lambda and natural frequency, where there's a very clear value of fractional distance at which the maximum frequency happens. This is seen by the fractional distance of 0.4. having the largest magnitude at every natural frequency. For the pentagon structure, we see a similar nonlinear behavior, but now the maximum is at lambda 0.5. We don't see as large of a difference in magnitude for the structures, with the maximum frequency at less than 400, while with the triangle the max was over 800. The nonlinear relationship is also much lower in this, and a much lower change for all the natural frequencies. One thing to note is the structure on the side is roughly the Sierpinski pentagon. Every regular polygon has a Sierpinski number, which is related to that lambda. We see a similar nonlinear trend between natural frequency and lambda, with a continuing decrease in value of natural frequency. With the first natural frequency, the value does not change much, at around 25 Hz between each test. We also see a maximum at 0.5, which is the same as the last test with the pentagon. With the octagon structure, we continue to see a decrease in natural frequency and a flattening out of the curve between lambda and natural frequency. There is very little change between the structure's natural frequencies as lambda increases. While the maximum is not much different, the difference between values at the maximum and minimum for each natural frequency is much lower. These results have highlighted several things in future directions for this work. The most important result from our work is that the statistical self-similarity from the chaos game does lead to similarities in mechanical properties. Now that we have this observation, we can generate sets of structures which we know to have similar properties, at least in terms of its modal frequencies. This can be done in a complementary approach to inverse generative design methods, since it allows for some level of forward design. Another point of discussion is that an increase in the number of sides of the polygon leads to a decrease in the value of the natural frequency. This can be seen when comparing triangle and hexagon, where the difference in maximum values is more than double. There's also a nonlinear relationship between the value of lambda and natural frequency. This was most apparent in the triangle case. In the future, there are several things we'd like to look at testing, such as non-convex polygons. This can be done through triangulation of the structure in order to use the chaos game, since the chaos game can't be used on concave polygons. We would also like to look at changing the rules for the chaos game, such as the vertex chosen can only be the non-adjacent vertex to the last one chosen. This is that example shown here. We would also like to use other testing methods for the structure to determine if there are similarities in other mechanical behavior. This example is pulled from our journal extension of this work, where we conducted tensile testing of the structure. This will be published soon, and you can look at it there. We also think that an exciting future direction is using the chaos game as Voronoi sites for generating 3D foam structures. Overall, our testing showed there is a generative design space using forward design with the chaos game, with a relationship between the parameters and their natural frequency. There is also a rich design space in the future for other testing and generation methods. Thank you for listening to our presentation. We discuss many more results and specifics of our method in our paper.